Hey, hello, students. I hope you guys are doing good home. So today, I'm going to record a video. But I think it's going to be two video clips for lecture 15. So in this lecture, we're going to talk about uh, uh, two different reactions for transition metal complex. So the first one is let's choose a different color. So the first one is redox reaction of transition metal complex. The second one is photo reaction of transition metal complexes. Yes, okay. We'll talk about the redox reaction first. So what's a redox reaction? Redox reaction is, so you have your metal complex supported with ligand. So it undergoes either reduction, the first one is reduction, or reduction means you add electron to transition metal complex. So you make your product just one negative charged. So you can also do oxidation reaction. So you remove one electron, so your complex will increase a positive charge. Okay. So in terms of the redox reaction, either you reduce your metal compound or you oxidize your compound. So it can adopt, this reaction can adopt two different mechanisms. So the first one is going to be inner sphere mechanism. So what's the inner mechanism? So inner mechanism means the reaction. So when you reduce oxidize your compound by one electron, then the reaction occurs with a bridging ligand, with the ligand, and bridging to your transition metal compound. Also, that is bridged to the reductant or oxidant. So we will use example to show you what does that mean. What's a bridging ligand for this type of transfer reaction? Okay. So another mechanism is we call outer sphere mechanism. So in outer sphere mechanism, that means when there's no bridging ligand between your transition metal compound and another reductant or oxidant. Okay, that just course the electron just course between two, Okay, I'm going to use this quiet bridge complex to show you what bridging means. What's how a bridging ligand affect inner sphere electron transfer. So here, so we have a cobalt complex bridged by chloride with a chromium complex. Say the cobalt started with, it's going to be cobalt ammonium ligand 5. Then you have a chloride ligand here. All right, so that's going to be the cobalt 2 overall, because that's here it's cobalt 3. Okay, because the chloride is in. Okay, so that's the transition metal complex, and then we have chromium 6 ligand. Okay, then we have that's going to be overall 2 plus. So that's a transition metal reductant. Okay, so I'm going to show you how the chromium reduce this cobalt penta-ammonium chloride complex through this bridging chloro complex here, shown here. Okay, so here, so this one, Okay, so that's chromium. Here is a living water, and here is our cobalt complex. Here, this one is chloride. Okay, so initially they are separate. Then when they approach to each other, so they form a kind of, you can call it a transition state. Okay, a kind of um, approaching complex, and then so the water from chloramine will go away. Okay, will dissociate from the chloramine. Okay, so then you form the open side from chromium will be picked up by chloro ligand from cobalt. So this side is still chromium. So this one is cobalt. Right now chloride is bridging these two parts, and then when they form this bridging core complex, the electron will move from chloride to cobalt. So you can see we have initially the chlorine, the chromium metal has green color. That means has an electron there, and then after complex formation here, you see cobalt become green color. That means electron, move from chromium to cobalt. Okay, and then this chloro bridge complex will dissociate, and then the chromium will pick up this water ligand goes back, and then you get fully separate two species. So that is going to be in this state. So we are going to have chromium water 6, but right now because since it's losing electron, it's going to 3 plus, and here the cobalt is going to be cobalt and 3 5, and coral is going to be become plus here. Right now cobalt become 2 plus. Okay, you see redox change or redox change. I can add the initial state. Okay, here is chromium water 6. Then we have that's going to be 2 plus. Right, so here is cobalt. Cobalt we have cobalt 3 plus. 1 5 3 5, and chloro as 2 plus. So you can see after reaction through this intermediate. Okay, that's important. So inner sphere. Okay, that's inner sphere electron transfer. Then you get the cobalt reduced to cobalt 2, chromium become chromium 3. So that's a mechanism. That's a mechanism. So another thing I want to point out is it's going to be marked by my writing up, but the point is, so for this reaction, this one, maybe the formation is bridge complex, maybe the major barrier. Okay, major barrier, but also can other step can be the barrier. Okay, can be the written limiting step. Okay. All right. So that's how this bridge ligand to trigger the inner sphere redox reaction between two transition metal complex. And then this table, I'm going to show you how the bridge ligand affected the reaction rate. Okay, the first example here is kind of the background reaction. So here we don't have bridge ligand, no bridge ligand. So if you look at the reaction rate, it's 8 minus 10 minus 5. It's pretty slow. But when you start to have bridge ligand introduced to, cobalt species, okay, then what we are going to have is, you see the rate become significant increase, okay, become 2.5 times 10 minus 5. And then when you go to chloride, you can see slight increase. And if you go to iodine, it's even increase, okay, even increase. And if you use other, that's up to here, okay. If you use other bridging ligand, you get different reaction rate. Okay, so that shows you how bridging ligand affected reaction rates. Okay, here is another example. That's chromium compound. Okay, two chromium compound redox reaction. Okay, so you will see the rate is about this number, 7.4 times 10 minus 3. Okay. So also you can also use other type of bridging ligand instead of halide. Okay, you can use here is pyrazine. So this can bridge the metal one. So you can this one can coated with metal 2. So same thing here, you can use 4,4-bipyridine, okay, 2 nitrogen, they have a lone pair here. They can coat it with 2 different metal, okay. And same thing here, so we have amine here. They can coat it with 2 different metal. Metal 1, metal 2, okay. So you can use this type of bridging to trigger on this inner sphere redox reaction between 2 transition metal species. Okay. Okay. Let's move on. Talk about outer sphere redox reaction. So outer sphere reduction does not involve a bridging ligand. No bridging ligand. Okay. No bridging ligand. It's just when the 2 species. So here. So that's reductant here. And reductant, so that's oxidant. Okay, so when here the purple sphere means electron sitting there. Okay, so when these 2 transition metals, when they approach to each other, so the electron will adopt an electron tunnel effect. Okay, between 2 reactants and to trigger on the electron transfer. Okay, and then you end up with this side, the right side species to host electron here. You see redox change, right? So this side from 2 plus to 3 plus, and this side is 3 plus to 2 plus. Here you get the electron, here you minus electron. So that's a inner sphere. So no bridging ligand involve this reaction. Okay. So for this reaction, so I'm going to show you a little bit of the reaction coordinates. So that's kind of little advanced concept, but you don't need to how to say the it's not required for testing for sure. You can try best to understand this scheme. Okay, the reaction scheme here. So you can see here we have the purple curve is energy curve for reactant. Okay, reactants, and the blue curve is for the product. Okay, product. So here is the here. So that's reactant. Here is product. Okay, so they involve two species. Okay, so that's energy. The purple one is energy curve for the reactants 2 species together, and the blue curve is a energy curve, potential energy curve for the products. Okay, 2 species. Okay, then what happened is you will say the reaction barrier. So that's the starting free energy, and here is your ending product friend. But you will see, so here there's the delta G. That's a transition state. And so when you have to, that's a basic barrier overcome. So there's another term called the delta. Delta is called so we use next slide. That's easier to see. Okay, so delta here is called reorganization energy. It's not only involved, that's energy in energy change involve reactant and also solvent. So that's kind of solvent as environment. So that's an overall change for the whole system, not reactant, also environment. So what does that mean is, so your reaction has to overall, involve this type of energy. So here the delta G double dagger is in only the energy change you required for your reactants to allow the reaction to occur. Okay, so the delta is a total energy change, including reactant, also environment. Okay, so so you have the total energy, reactant, environment, the solvent goes here, and that's your reactant state, and then you relax, and then go to here, and so that's your transition to the point, and you end up with the formation product at this point. Okay, so it's kind of advanced concept. It's about transition state theory for ion transfer, uh, reactions, and in fact, this scheme not only apply to out sphere transfer redox reaction, also the